So, good day everyone. I am Angelo Mendez, and my following group mates members are Anton Earl A. Lim and Cedric Hernandez. And in this video, we're going to tackle about the problem number 7. So, in problem number 7, consider a steam power plant operating on the ideal Rankine cycle. The steam enters the turbine at 5 megapascal at 350 degrees Celsius and is considered in a condenser at a pressure of 15 kilopascal. In this problem, we have to determine the thermal efficiency of the cycle and what would the thermal efficiency be if steam were superheated at 750 degrees Celsius instead of 350 degrees Celsius. So in the given, P1 is equals to 5 megapascal at temperature one of 350 degrees Celsius. Then P2 is equals to 15 kilopascal, and at the conversion of megapascal over 1000 kilopascal, it is 0.015 megapascal. And for the B is the P1 is 5 megapascal at temperature 1 instead of 350 degrees Celsius, you have the 750 degrees Celsius. So for the P2, we have 15 kilopascal, then convert to megapascal over 1000 kilopascal, then you'll have a 0.015 megapascal. So for the schematic diagram, you have here uh, from the boiler, process 1, steam goes to the turbine, and process 2, from the turbine, steam goes to the condenser and the pressure is condensed. Then process 3, steam is condensed and goes to the pump, and the condensed steam is pumped back to the boiler. Now for the here TS diagram, you have the for the TS diagram, we have the process 4 to 1. A high pressure steam is generated to 5 megapascal at 350 degrees Celsius. Then goes to the turbine in the point 2, and process 2 to 3 goes isentropic process. Then the process 3 to 4 is condensed. So we solve for the X here. Then because it is in wet region, then the process 3 to 4 is the steam pumps to the boiler and it undergoes again isentropic process. So as you can see here in the steam table, you have there your give the following values being underlined. Then for here, uh, the steam table is superheated steam. Then temperature of 750 degrees Celsius. So first in the first state 1 solution, we have the from steam table, the pressure 1 is that it is to equals 5 megapascal at 350 degrees Celsius. So your H1 there is 3068.4 kilojoule per kilogram, and your S1 there is 6.4493 kilojoule per kilogram. And for your state 2 there is that the pressure 2 is equals to 0.015 megapascal. So since S1 is S2 is since S1 is equals to S2, since process 1 to 2 is an isotropic process, because the process 1 because the process 1 and 2 is an isotropic process. So from steam table to stable, pressure 2 is equals to 0.015 megapascal. Then your SF there is 0.7549 kilojoule per kilogram, SG of 8.0085 kilojoule per kilogram. Then you'll have your dryness fraction of X is equals to equation there of dryness fraction of X is equals to S2 minus SF, then over SG over SF. Then all you have to do is substitute there 6.4493 kilojoule per kilogram minus 0.7549 kilojoule per kilogram, then the 8.0085 kilojoule per kilogram minus to 0.7549 kilojoule per kilogram. So you'll have the result answer of dryness fraction of X is equals to 0.785, or the percentage of X is equals to 79%. So here in H2 is equals to HF plus drainage fraction and HFG. So from the same table, pressure flow is equals to 0.015 megapascal. You have your HF there is equals to 225.94 kilojoule per kilogram, and your HFG there of 2373.1 kilojoule per kilogram. Then your H2 there we have is equals to 225.94 kilojoule per kilogram, and plus the your HF and your HFG, which is the 0.7785 multiplied to 2373.1 kilojoule per kilogram. Then you'll have the answer of H2 is equals to 2088.8.8235 kilojoule per kilogram. So in the state 3, we have the P3 is equals to P2, uh, which is the P3 is equals to 0.015 megapascal. So the H3 to HF at 0.015 megapascal is the H3 is equals to HF because process 3 is the pump, and this is where the pump touches the saturated liquid line. So we'll have the H3 there is equals to 225.94 kilojoule per kilogram. In the state 4, P4 is equals to P1, then is equals to 5, P4 is equals to 5 megapascal. So in the process in the process 3 to 4 is a also a asymptotic process. So S3 is equals to S4, then you have there is equals to S3 is equals to SF at pressure 3 over I is equals to 0.015 megapascal. So you'll have the answer of the S4 there to 0.7549 kilojoule per kilogram. So the work pump there is equals to V3, then P4 minus P3. So uh, the uh, from statement table you have the 0.015 megapascal, then you have your VF is equals to 1.0141 um, m cube over kilogram, and your VG there of 10.022 m cube over kilogram. Then your V3 or is equals to 1.0141 m cube over kilogram. Then the work pump in is that you have the substitute there, then you have the is equals to 1.0141 m cube over kilogram. Then substitute the P4 and P3 there, you have the 5 megapascal is equals to 0.015 megapascal. Then you have the answer of result of work pump in is equals to 5.05528885 kilojoule per kilogram. So same thing here, the work pump in is equals to H4 minus H3. H4 is equals to H3 plus the work pump in. So the H4 is equals to 225.94, then the kilojoule per kilogram plus 5.005552885 kilojoule per kilogram. Then the H4, you'll have the answer there of 230.9952885 kilojoule per kilogram. So the heat added or the Q in is equals here in here the Q in or heat added is equals to H1 minus H4. You have to substitute it. The heat added Q in is equals to 3068.4 kilojoule per kilogram minus to the 230.9952885 kilojoule per kilogram. So you have the answer of heat added Qn is equals to 2837.404712 kilojoule per kilogram. So in here the uh, turbine work turbine out, you have is equals to H1 minus H2. So the turbine work turbine out there, you'll have is equals to 3068.4 kilojoule per kilogram minus to the 2088.8235 kilojoule per kilogram. Then the answer of the work turbine out there, you have a result of 979.5765 kilojoule per kilogram. Then the heat going out, yeah, is equals to H2 minus H3. Same thing, you have to substitute. So Q out is equals to 2088.82 0.835 kilojoule per kilogram minus 225.94 kilojoule per kilogram. So you'll have the answer of the heat out, going out, or the Q out is 1862.8835 kilojoule per kilogram. Then uh, to in here the thermal efficiency, so n is equals to 1 minus the heat going out over heat going in. So all you have to do is to substitute the heat that is going out and going in, q out and q in. So n is equals to 1 minus 1862.8835, and your Q in, which is the 2837.404712 kilojoule per kilogram. So you'll have the result there of n is equals to 0.3434 or 0.34, or in the percentage of 34%. So in here, uh, so so in here you have there your schematic diagram with the answers, and you have the Q in, which is the heat going in, which is the 2837.404712 kilojoule per kilogram, and your work turbine going out is 979.5765 kilojoule per kilogram, and heat going out here is 1862.8835 kilojoule per kilogram, and your condenser of pressure to of 0.015 megapascal. Then your work pump in here is 5.055288 kilojoule per kilogram. So for the TS diagram, you have same thing. Here all you have already there your answer. So you have the heat going in with Q in 2837.404712 kilojoule per kilogram, and also the work turbine out, which is 979.5765 kilojoule per kilogram. Then the Q out also here of 1862.8835 kilojoule per kilogram. Then also you have also your work pump in, which is the is equals to 5.05528885 kilojoule per kilogram, and your pressure to also here of P2 of 0.015 megapascal. So in here, same thing. They have the answers already there. Just like what I discussed earlier. Then you have already there your answers. Boiler T1 of 750 degrees Celsius and your P1 of 5 megapascal. Then also your TS diagram. Then here in the problem B solutions, for the state 1 from steam table, which is pressure 1 is equals to 5 MPa, then is at 750 degrees Celsius. Then your H1 there is equals to 4018 0.5944 kilojoule per kilogram. Then your S there is equals to 7.6321 kilojoule per kilogram. In the state 2, we have your P2, pressure 2 is equals to 0.015 megapascal. Now since S1 is equals to S2, process is an isentropic process. So from steam table, P2 is equals to 0.015 MPa or megapascal. Your SF there is equals to 0.7549 kilojoule per kilogram. Then your SG is to 8.0085 kilojoule per kilogram. Then in getting our dryness fraction, it is the X equation here, X equals to S2 minus SF over SG over SF minus SF. So same thing, you have to substitute, which is 7.632 kilojoule per kilogram minus 0.7549 kilojoule per kilogram over 8.0085 kilojoule per kilogram minus 0.7549 kilojoule per kilogram. Then you'll have the answer of dryness fraction x is equals to 0.9481, or the percentage of x is equals to 95%. So in H2 is equals to HF plus drainage fraction of HFG. So from the steam table, P2 is equals to 0.015 megapascal. You have your HF of 225.94 kilojoule per kilogram, HFG of 2373.1 kilojoule per kilogram. Then you have the substitution there of 225.94 kilojoule per kilogram plus 0.9481 multiplied to 2373.1 kilojoule per kilogram. Then you have the answer of H2 of is equals to 2475.87611 kilojoule per kilogram. So in the state 3 of the problem B, you have the P3 is equals to P2. So since P3 is equals to 0.015 megapascal, then H3 is HF is at 0.01. H3 is equals to HF is at 0.015 megapascal. So we have the answer or result of H3 is equals to 225.94 kilojoule per kilogram. State 4 of P4 is equals to P1. So P4 we have is equals to P5 megapascal. So process 3 to 4 is an isentropic process, right? So S3 is equals to S4. So S3 is equals to SF at pressure 3 is equals to 0.015 megapascal. So you'll have the answer of 0.7549 kilojoule per kilogram. So same thing here, the work pump in the V3 to P4 minus P3. So V3 is equals to VF at pressure 3 is equals to 0.015 megapascal. So from the steam table of 0.015 megapascal, you have your VF of 1.0141 m cube over kilogram and your VG of 10.022 m cube over per kilogram, and V3 of 1.0141 m cube per kilogram. So substitute there, substitution of work pump in is equals to 1.0141 m cube per kilogram to 5 megapascal minus to 0.015 megapascal. So you'll have the answer of work pump in of 5.05528885 kilojoule per kilogram. So here in a work pump in of H4 is minus to H3. So H4 is equals to H3 plus the work pump in. So H4 is equals to 225.94 kilojoule per kilogram minus the work pump in of 5.0552885 kilojoule per kilogram. So the H4 there, you have the answer of 230.9952885 kilojoule per kilogram. So the heat added here, Qn, the H1 minus H4, you have the heat added is equals to 4018.5944 kilojoule per kilogram minus to the H4 of 230.9952885 kilojoule per kilogram. So you'll have the answer of heat added of 3787.599112. So here you have already the turbine out of H1 minus H2. So turbine out is equals to work turbine out is equals to 4018.5944 kilojoule per kilogram minus to 876116 kj per kilogram, kilojoule per kilogram. So work turbine out is equals to 1542.7141829 kilojoule per kilogram. That's your work turbine out. So for the heat going out, H2 minus H3 is equals to the heat going out of 2475.87611 kilojoule per kilogram minus 225.94 kilojoule per kilogram. Then you have the answer of heat going out of 2249.93611 kilojoule per kilogram. So your thermal efficiency of N is equals to minus the heat going out over heat going in. So you have the one heat N is equals to 1 heat going out 2249.93611 kilojoule kilogram over 3787.599112 kilojoule per kilogram, which is the heat going in. So you have the answer of N is equals to 40597, or the percentage of N is equals to 40.6%. Then there you have already your TS diagram with its answer, which is the heat going in, which is the 3787.59911 kilojoule per kilogram, and the work turbine out of 1542.71829 kilojoule per kilogram. The heat going out of 2249.93611 kilojoule per kilogram, and also your work pump in, which is the 5.0552.885 kilojoule per kilogram. Then your schematic diagram, same as earlier, same thing. Then you have already there your heat going in, which is 3787.599112 kilojoule per kilogram. Then the work turbine out is which is the 1542.71829 kilojoule per kilogram, and your uh, heat going out of 2249.93611 kilojoule and per kilogram. Then the work pump in there of 5.0552885 kilojoule per kilogram. So that's it for the discussion. Thank you.